Swayam Prabha. Digital India. Educated India.
So today we want to see public key encryption based on this assumption, and this is a very famous scheme. It's called El-Gamal encryption. Okay, so we have this key gen algorithm here, and this is supposed to output a public key and a secret key, right? And then we have encrypt, right, which should take the public key and some message, and it should output the ciphertext. And then we have decrypt, which should take the secret key and the ciphertext, and it should output some message, right. So this is what we need to construct. So let's build this. Okay, so what we'll do is we will select the group as we saw in the DDH assumption. Okay, so let us choose G of prime order Q with little g as the generator. Okay, so this is step 1. Now sample X. I wonder if I should give it a different name. Okay, I guess it doesn't matter. So now sample X from ZQ. Compute X is G to the X. And now what should be my public key? So G and X, which is G to the small x, and the secret key is small x. So it's what you would expect, right? So basically we saw the key exchange protocol. So you would expect that, well, what you want to make public is some instance of discrete log, right? So I have G. So it's very natural that if I want to make something public, I may as well choose G to the X. So this is just a intuition for how to construct schemes, right? So basically I need to choose something which is secret and something which is public. So the logical thing to do is to sort of whatever problem I am relying on, right? I would want to keep secret as whatever is hard to compute, and I'll make public whatever the secret is hard to compute from, right. So G to the X does not easily give me X by the discrete log problem. So this is how we sampled it. So now what about encryption? So one thing here is that we let M be a group element. Okay. So why is this okay? Like if M is some arbitrary string, I can still hash it down to some group element. So let's just think of, and by the way, the group is huge, right? So it's not that I'm going to be short of messages. So if M is in the group, then let me sample a random R. Now this has to happen somewhere, right? Because we already discussed how encryption has to be randomized. So I will sample some random R, and I will set C as C1, C2, where C1 is G to the R and C2 is M times X to the R. Now just note one thing over here. So X is what? It is G to the X, right? So X to the R is what? It is G to the XR. So you can see one nice thing happening already, that by the decision Diffie-Hellman problem, this G to the XR should be indistinguishable from G to the truly random C, right? And my message M is being masked by this term, correct? So, my message is in the group and I am doing a sort of group operation with a random element. So, if I take a fixed element and a random element in a group and I perform the group operation, I will get in a finite group, I will get a random element, right. So, this is already an intuitive way to see why this C2 should be secure. And the DDH assumption lets me give out G to the A, G to the B, right. So, it is not a problem here that G to the X and G to the R are also output, right, because the DDH assumption tells me that given G to the X and G to the R, G to the XR is indistinguishable from random. The whole tuple is part of the distribution. Okay. So, how will I decrypt now? So, decryption is quite easy, right. So, I have G to the X. So, what should I do? So, if I just compute C2 divided by C1 to the X, what will I get? So, this is M X to the R divided by G to the R the whole to the X. So, this is nothing but M times G to the XR divided by G to the XR, right. So, I just get back in. So, the scheme is correct. Okay, so correctness holds. Can decryption fail with negligible probability? What do you think? Okay, I will let you think about that. So, now we want to prove security. So, in particular we would like to show some theorem. The El-Gamal encryption scheme satisfies IND CPA security if the DDH assumption holds in group G. Okay. So, what do I need to do now? So, assuming that I'll argue it by contrapositive. Okay. So, assume there is an attacker against the El-Gamal encryption scheme. I will use that to construct an attacker against the DDH assumption. Okay. So, I will construct what we call a reduction, which will take as input an instance of the hard problem DDH. So, what is an instance of the hard problem? So, you should get G, G to the A, G to the B and a third element. This third element, it could either be G to the AB or it could be uniform, and I do not know which one it is. So, what I want to do is I want to somehow plant this question into the encryption scheme and feed it to the attacker. So, if the attacker can crack the encryption scheme, then I will use the attacker's answer for the bit. Remember, so the attacker has to output a bit in the end, right, whether it got encryption of M0 or M1. So, what I want to do is I want to take an instance of the DDH problem and I want to somehow sort of fit it into this encryption scheme. so that I give it to the attacker, and I want to claim that if the attacker guesses the bit correctly, then I can also guess the DDH bit correctly. I can also decide whether the DDH tuple has real or random. Real means G to the AB, random means G to the C. This is what I would like to do. Okay, so very good. So, you know, what should we do? So, let's set this up. Okay, so suppose A is an adversary with some non-negligible advantage. So, we defined this earlier, right. So, basically it guesses the bit correctly with something over a half, right. So, that we call its advantage, and if this is non-negligible, right, then we say that the adversary is winning the game. So, I mean, then we say that then we say the adversary has broken the scheme rather. So, let us say that A is an adversary with a non-negligible advantage epsilon. We will construct a DDH distinguisher B. Okay. Thus, B takes as input, or maybe I should say here, G, G to the A, G to the B and T, where A and B were sampled randomly from ZQ, and T is G to the AB or T is random. So, now let us look at the steps, okay, that this B should do. So, now basically I have this A, right, this is my attacker A, this is, you know, against the El-Gamal encryption, and I have this B, you know, sitting outside it. So, this B has to interact with A as we described in this game, right. So, B has to play the role of the challenger to the adversary A. Okay. So, what does the challenger have to do? The challenger must give it first of all a public key which is distributed correctly. Now, let us look at what is the public key in the El-Gamal encryption scheme. It is G and G to the X, right. So, what is a very natural way for B to define the public key? Exactly, very good. So, I mean, think about it, right. I as the reduction, or I am supposed to play the challenger to A, right. I need to use the adversary A to break the DDH assumption. So, I better embed my DDH assumption in whatever the attacker sees, right. Now, when we saw previously, when we looked at the scheme, we made a note of the fact that the ciphertext is looking like a DDH tuple, not tuple, but like a DDH target element, right. So, the public key contains one part of the DDH tuple, right. So, the DDH tuple is what? So, if I ignore G for a second, it is G to the A, G to the B and G to the either A, B or C, right. So, the public key contains one of those things, right. So, what should I do? So, let me choose. So, B chooses Pk as G and X as G to the A, right. So, this is consistent with what this public key looks like. Now, note one very important thing in the real scheme that we saw. The key generator also knows the X, it knows the secret key. But here actually B does not know the secret key, and this is actually crucial, right, because I want to use the attacker to solve a hard problem which I do not know how to solve otherwise. If I myself knew the secret key, then I cannot use the attacker in any useful and intelligent way. Does that make sense? So, I want to use the attacker to solve the DDH problem. So, it better be the case that I do not know already the solution to the DDH problem, right. It better be the case that I cannot compute this discrete log. So, B will choose this as the public key. Okay. Now, as a next step, A outputs some M0 and M1 which are in G. Okay. And then what does B do? B now must compute the ciphertext, right. So, what does the ciphertext contain? It contains a C1 and a C2, where C1 is G to the R. Now, what should C1 be set as? The second part of the DDH tuple, right. So, remember that B receives G to the A, G to the B and T, right. So, now it is going to use the G to the B part as C1, okay, and the C2 it will choose a random bit B and it will compute MB and it will multiply this with the T, the third thing that it received. I mean the fourth if you count G. Okay, so it computes this. Now, A guesses the bit, right. So, let us say it outputs B prime. So, now what does B do? If B prime is equal to B, okay, then B says it is the real distribution, that is T is equal to G to the AB, else it says that this is the random distribution, that is T is equal to G to the C. So, let us analyze this. Okay. So, now this T is either equal to G to the AB or it is equal to G to the C. Now, first consider the situation where it is equal to G to the C. In this case, my C2 is MB times random, right. And if it is MB times random, that means that C2 is itself random, right. Does everyone agree? Because if the message is being masked by a truly random element, then this distribution is now independent of the message. So, in this case C2 is completely random, that means that information theoretically it hides the bit B. Okay. Is this clear to everyone? So, if the target element T was a truly random element G to the C, then this target element times the message is also truly random and it completely information theoretically hides the challenge bit B. So, in this case in fact the attacker cannot have any advantage. Okay. So, basically if the attacker basically guessed wrong, okay, then it makes intuitive sense, right, that if you could not guess, maybe it was you claim that you have an advantage in breaking my scheme, right. But if I give you something where the bit is information theoretically hidden, right, then obviously you cannot have an advantage, right. So, if you did not guess, then I will say that the target that I received was actually truly random. On the other hand, if you did guess, right? Then, well, you claim to, I mean, I have assumed that you are solving this, you are breaking this construction with a good probability, okay, and when when t is g to the ab, that is the case that C2 is MB times G to the AB, right. So, that is the case when C2 actually looks exactly like the ciphertext in the real scheme, right. So, if you broke the scheme, then it must be the case that the target element that I got was actually the DDH from the DDH distribution, that is, it must have been G to the AB. Okay. So, we can prove this formally. So, let's figure out what is the advantage of this adversary. Okay. So, let's wait. So, let's look at the probability that B outputs real, the probability that it outputs random. So, for real we will say that B outputs 1. Okay. So, let us look at the probability that B outputs 1 when T is equal to G to the AB. Okay. So, this is the probability that B is equal to B prime given that T is equal to G to the AB. In this case, this probability is half plus epsilon. Does everybody agree? This is because when the target element is G to the AB, right, at that time the adversary has an epsilon advantage. So, by definition of the adversary's advantage, we can say that when T is equal to G to the AB, the probability that B outputs real or 1 is half plus epsilon. Okay. Okay. So, now good. So, now on the other hand, what is the probability that B outputs 1 So, this is maybe I am being a little loose in how I am writing this, I will at least put arrow. So, B equal to 1 means that B outputs 1, I should say, the output of B is 1. Okay. So, the probability that B outputs 1 when T is equal to G to the C, this I claim is exactly half by the reasoning that we followed earlier, right, because if T is totally random, I cannot the adversary cannot do better than half and therefore neither can I. Okay. So, the advantage of B maybe here I will just write lambda. Is epsilon. This is just by definition of advantage. Okay. So, therefore, what we showed is that the advantage of A translates to advantage of B. Let us recap the argument if you have seen it for the first time. Okay. So, let us recap the idea. Okay. So the decision Diffie-Hellman assumption, which we said is like in the family of the discrete log type assumptions, but stronger than discrete log, in the sense that if you solve discrete log you can solve this, but the reverse may not hold. This assumption is saying that the following two distributions are computationally indistinguishable. I give you g to the a and g to the b, and as the last element I give you g to the ab, or I give you g to the c for random c. These are indistinguishable. Now our El-Gamal encryption scheme, what did it do? It used g and g to the x as the public key, and the x, the discrete log, it kept as the private key. Okay. Now, in order to embed the DDH assumption into the scheme, it is very natural that if I gave g and g to the something in the public key, it is very natural for me to give the remaining g to the something and g to the product in the encryption, right. There is nothing else, right, there is only encryption and decryption. So, all the attacker sees is really the public key and the ciphertext, that is all it sees. So, armed with that intuition, you can see that what will I choose my ciphertext to be. So, I will sample a random element r, I will compute g to the r, and I will compute now g to the r x, right. So, I have my public key g to the x, I raise that to the r, that gives me g to the r x. By the DDH assumption, this should be indistinguishable from random, right, and I use this to mask my message. So, this is my encryption, and obviously I can reverse this process and recover the message if I have the original discrete log, because the first component of the ciphertext, which simply has g to the r, now I can, just as in the key exchange, right, I can raise that to the x, get g to the r x, this is my masking term for the message, so I can cancel those out. Okay. So, this is my encryption scheme. Now, how do I prove security? So, security is following very intuitively, right, that is why this is a very good first example to see of a security proof. It is following very intuitively from this DDH assumption in the way that we discussed, but in order to write it formally, we just need to be a little bit careful. So, what we need to do is construct a reduction. So, where I construct some algorithm B that plays the challenger in this int CPA game. So, what should this challenger do? The challenger is playing with the adversary, right, and it is deciding whether the adversary won or not. But this does not in general say much about the security of the scheme, unless I can use the the work done by the attacker to solve some hard problem, right. Yeah. So, what I will do is I will take as input an instance of the DDH problem. So, that means g to the a, g to the b, and some element t, which is either g to the ab or it is random. Okay. And I will use this DDH tuple to embed it into my public key and ciphertext. So, the first g to the a I will give as the public key, right. The second g to the b and g to the ab slash g to the c, this I will give as the two components of my ciphertext. And I just need a little bit of care to argue that if the attacker wins in the game, if it guesses the bit b correctly, right, then I can also say that the DDH tuple I received would have been the real tuple. It would have been from the not the random distribution, but the g to the ab distribution, right. And this is why, this is because if it were random, then my message bit is information theoretically masked. So, in this case, no matter how smart my attacker is, it could not have had any advantage. This is the argument.